Hello guys, welcome to my series on pre-processing resting state functional magnetic resonance imaging data. In this video, we will see subject motion noise and then we will see how can we remove this subject motion noise using realignment. Further, we will see what is frame-wise displacement and how by using frame-wise displacement we can include or exclude a particular subject in our dataset for further analysis. Okay, so for the most of the part in this series, I will use SPM 12 toolbox in MATLAB. However, occasionally I would also use AFNI and FSL for displaying images of a certain other functions which are better over here. Okay. So let us first see the data. So this is a particular subject that I have chosen from a particular data set. I'll put the link of the data set that I have chosen in the description below, so you can also try it for yourself. So it consists of two folders, this particular subject. So every subject in that data set will consist of two folders. One is func. So the func has the functional images, or this is the resting state bold fMRI image. And then there is the anatomical image, that is the T1 weighted image. Okay, so I have not done any pre-processing now. So let us first see how does this image looks like, especially the functional image, and then let us see why we require pre-processing. Okay, so for that I will go to AFNI. I'll use AFNI to display the images because there are certain functions which are better in AFNI as compared to SPM. So for that I'll use this Windows subsystem for Linux because AFNI and FSL require Linux. They don't work in Windows. So you can also download this subsystem WSL, Windows subsystem for Linux, and then install AFNI and FSL over here. Okay. So if you notice, I am already in this directory. If you see the same directory where my particular functional data is present. So I just have to type AFNI and press enter. So AFNI will automatically load this particular image. Right, so this is how the image looks like. This is the pre-processed functional image, the raw functional image of this data. So this is the 3D MRI scan. Also, because this is a 4D data, because the resting state is a 4D data, you have X, Y, Z and time. So to visualize time, there is a very good thing over here known as graph. So over here, what this graph does is you get the time series of the voxel that are in this box. Okay, so this is a very nice feature of AFNI. Okay, so now see, this is the this is the raw data that we have over here. Now you can see, especially over here, there are these dips at certain places in the data, right? Also, you can navigate through this particular image in time by just pressing the arrow, the left right arrow key on your keyboard. So if I do this, you can see a video is playing in some sense. So you can see that there are some voxels changing over here, right? So up till here there is no problem. You can see, I mean, it should be like this, that your image, it should look like this is all still and only over here there is some fluctuation, right? But look what happens when we come over here at this dip. Okay, so here we are changing till here, it is okay. As soon as I go across the dip, you see there is this motion. Are you able to see this? So you can see this particular thing just goes up by certain distance and then comes back down. This is the motion artifact that that is faced in fMRI. So whenever you move a little in the MRI machine at that point of time you get to see this particular artifact. Okay, so this is the first thing that we are going to remove using something known as realignment. Okay, so let's see how can we do that. So this is the motion artifact. So for that we'll go in MATLAB. So this is MATLAB, and over here we'll type SPM fMRI. So I have already installed SPM in my MATLAB. Right, so we are in SPM. Now what we are going to do is, first we are going to see what is realignment. So if you just click over here, you get 4 options: realignment, estimate, reslice, estimate and reslice, and unwarp. So so mostly people nowadays don't use unwarp, because this is actually related to something that some artifacts that were during the EPI scans, and nowadays the MRI scanners are more advanced, which actually remove those what we say artifacts beforehand. Okay, so we normally don't use unwrap now, because that is taken care by the scanner. So our interest will be in estimate and reslice. Okay, so there are 3 options now: estimate and reslice, reslice and estimate. So we will actually most probably focus on estimate and reslice, but I'll also tell you what happens in these two a little later. Okay, so for now let us just see what is reline, estimate and reslice. So when you click on estimate and reslice, a batch editor opens up, and there's a lot of things that you have to put in over here. Okay, so first it tells you data, so it needs data. Alright, so before that let me just tell you what is realign. So by realignment, what will happen is, this particular software in SPM will realign the scans to a particular image. So over here it says register to mean. So what will happen is, it will take the mean across the time points. So we have these different time points over here. So there are 152 time points that you can see over here. Right, so so here if you see the index, so here it says 151. So it also starts from 0, so 0 to 151, that means total there are 152 time points. So what it'll do is, so it'll first take the mean of all these time points, and you will get a 3D image which is the mean across time points, and that is the option that is selected over here, register to mean. All the different slices will be registered to the particular mean image. Okay, so that is what is going to happen. So for that, first we have to get the data. So double click over here. So you have to so this is a session, so double click. Right, so now go to the particular folder. So my folder is over here. Go to the functional image. So this is only one, so this only gives you the first slice. So to get all the 152 slices, what you do is, or 152 volumes, these are not slices but volumes. So just type any number which is greater than 152 over here and type enter and press enter, and you will get all the different volumes that are present over here. Okay, you can either right click and press select all to select all these particular volumes, and then press done. Okay, so here we have all the 152 files. Okay, now these are certain other options that you can see. So here there is quality. So highest quality one gives the most precise results, whereas lower quality gives faster realignment. So here there's a trade-off between how much time you want to put and how good quality of realignment you want. So the default is 0.9, which is in most cases preferable. Then there is separation. So this tells you, so for realignment you actually need some points. you have to select some points in this image, and then those points are mapped from one image to other. So this is the grid separation. If you not going in a lot of detail, so you can just keep these default values as it is. If you want to know more, you can go to the SPM manual and then see what actually everything is about. Or you can also read these things over here. These things are also very informative, so you can understand in most sense, in most cases, what is happening. Then you will have, so here this is the smoothing parameter, so it will smooth with some Gaussian smoothing kernel, and this is in millimeters, so we are applying a 5 millimeter Gaussian smoothing kernel. So these are some things that if we'll not go in much detail, but if you know, you can change, but for most of the cases these default values are okay. Then over here there's an option, either you can register it to the mean, or you could also register it to the first volume, the first volume that is over here. So this is again your choice. Registering to first will be a little more faster, because then it will not have to calculate the mean, but register to mean is a better option because it is a better representative of all the volumes. Then this is the interpolation technique. However, the default values are fine. We don't need any warping. We don't need to put any weights for a particular this image, so this 0 is okay. And then reslice option, so again these are also fine. Let us just keep them as it is. These are the default values. And then there is a file name prefix, so you will see that in the resultant output you will see there will be an R appended in the beginning, so this is a prefix. Okay, so just after you have put the data over here, and if you want you can change these things and see, and then press run. So as soon as you press run, you will see that SPM is trying to do something over here. So it is registering images. Right, so here you can see the result. So over here these graphs tell you how much is the displacement in a particular direction. So you can see that in the x direction, the blue line represents the displacement in the x direction. The green tells you the displacement in the y direction, and the red tells you the displacement in the z direction. Over here you can see that this particular point, this particular time point, so this is at an index of 47. You can see very well that this particular SPM also detected that it has some unusual movement over here somewhere close to 47. You can see that over here. Also there was not only a z direction movement or z translation, but also a rotation. So these three things are the rotation, the pitch, roll and yaw, the colors respectively. So here you can see that the pitch, there is a change or motion in the pitch direction or the pitch rotation. You can see that over here. So it has detected or estimated. So this is what estimate does. So estimate tells or tells us or estimates the different motion parameters, so the translational and the rotational parameters that has occurred in the different volumes over here. Okay, and then reslice actually gives you an image, a new image with a prefix of R, which will reslice all the images, and it will take care of this motion. So in the new resliced image there won't be any motion. So let us just see that output now. So first let us see. So here you can see initially there were only two files, the raw data and the JSON file. So the JSON file actually tells about the data over here. I forgot to tell you about this. Let us just see this as well. So depending on the data set, you may have a JSON file or you may not have a JSON file. So this tells you about the basic parameters of the MRI scanner that was used to um, scan this particular subject. Okay, so these are basic parameters. Okay, so now you can see after realignment there is this mean image that is first over here. So the mean image is all the different volumes are registered to this mean image. Okay, then there is a rp sub .txt file. So if you see this particular file, this actually gives you the values of the different motion parameters that were displayed over here. Okay, so the first three columns correspond to the three x, y, z direction translation, and the last three columns correspond to the rotation parameters, pitch, roll, and yaw over here. And okay, so let me just open this in Notepad++, so that you can see that there are 152 such rows. So the 152 corresponds to the 152 volumes that we have. Okay, and for each volume, how much is the x displacement, y displacement, z displacement, and the pitch, roll, and yaw values over here. Okay, so this will be useful to understand where is the motion here, where's the motion, right? So that is this file over here, and then there is this r sub that we have. This r sub is the output or the motion free image that we have over here. Okay, so let us just go back to AFNI and look at our motion free output. Okay, so just I'll type underlay, and then here you can see the r sub. Right, so now this is, let me again go to the graph. Okay, the graph is open over here. However, you can see there is still a dip over here, but when you again just look at a movie, so let me just, yeah, you can see the voxels are changing inside this particular thing. But now when I go across the drip, you can see that now the motion has reduced. This dip now is actually because of the color change. So in this particular place or this particular volume, there was also a color change that happened. So I'll again show you. You can see there was these some artifacts over here, because of which so in some sense these are white over here, and suddenly they become black. Okay, now this is not motion, this is not because of this is because of motion, but the actual motion has gone. So if I just again show you the original image, so now look at the dip over here. Okay, so you can actually see that this is moving up over here. See, so this thing is moving up, right? But on the other case over here, if you see the registered image, here you won't see that. You see, it is only the voxels that are changing. This whole volume is not going up. You can see that. So this is the realignment output that we have got, and then things are okay. So after realignment, you can see that all the motion changes will be gone, but still this is again an artifact which can cause problem while analyzing the particular data. We will see how we can remove this as well in our future videos, but for this video the only goal was to remove the motion problem, or the subject motion, right? So that is what realignment has done. Okay, we will remove this in other videos as well. Okay, so this was the realignment output. Now let us see about the frame-wise displacement. So I have written a script for a frame-wise displacement over here. I'll put this in the I'll put a link to this script in the description below. You can also see that over there. So what this script does basically is it will load the input text file, that is this file, this one, that has all the values of the XYZ displacement and the rotation, pitch, yaw, and roll displacement values. And given this particular script, it will tell you whether is the motion okay. I mean, if it is okay, you can actually use this for further analysis. But then there are some subjects where the displacement is a lot. So over here, if you see, so if I just want to give you a reference, so this particular image that I have, so in SPM also you can actually view the image, but I use AFNI because it has those graphs and all those sorts of things which are better. SPM does not show you a graph over here. Okay, so over here this is the header. Okay, so this is a nifty format image, and a nifty format image also has something known as a header, nifty header. So these are the some of the values which is there in the nifty header. So this particular image has a nifty header. So it has something known as a voxel size. So you can see the voxel size for this particular image is 3 cross 3 cross 4. That means in the X direction, the voxel is 3 millimeters long. Okay, a voxel is an volumetric pixel, so a small unit over here. So the voxel over here is 3 millimeter long. Okay, 3 millimeter in X, 3 millimeter in Y, and 4 millimeter in Z. Okay, so in some sense, a motion of 3 millimeter or less is okay because it is still within the voxel limit. However, if a particular subject has moved more than 3 millimeter, say it has a motion of say 4 millimeter or 5 millimeter, then we will have to exclude that subject from our analysis because it is not appropriate to actually use that for analysis. Any outcome that we get from that particular subject may or may not be true. Okay, so only if it is within the voxel range, it is fine. If it is above the voxel range, then we may have to discard that particular subject. We cannot use this subject for for analysis if the motion is more than the voxel size. Okay, so this script actually tells you whether to include a particular subject or to exclude that particular subject. Okay, so this is a more better way. So one way is just look at these graphs, right? The X, Y, Z and pitch roll, this graph. So one thing is just put a threshold, and if there is any motion above that particular threshold, like in this case, say, so don't keep a threshold of 3 millimeter. That would be too high a threshold. So say 2 millimeter or say 1.5 millimeter is a good threshold. So 1.5 millimeter. So if there is any motion above 1.5 millimeter, then remove that particular subject. That is one way. The other is using the frame-wise displacement. So this is the frame-wise displacement script. Now let me just go through this once, and what I'll do is I'll put a breakpoint over here so that I can explain what is happening at every line. Okay, so initially the program starts from here where I have initialized a REST folder, which is actually the folder where my files are. So this is my REST folder. So let me just run and simultaneously execute each and every step and explain it to you. Okay, so here you can see the arrow is over here. So the program has run till over here. So you can see there is a variable named rest folder and it has the path to this folder. Okay, so that is what has happened. Now in this line rp rest equals load, what are we going to do is we are going to load this text file, this over here. So the folder path is from here, and then I am giving it the name of the text file. Okay, so when I press step, so you can see there will be an rp rest variable which has the values of this text file. Okay, so it has 152 rows corresponding to the 152 time points and 3 columns, because the first 3 belongs to the translation, the last 3 belong to rotational. So we can say this is X, this is Y, this is Z, this is pitch, yaw and roll accordingly. Okay, so now that was about rest. Now here what we are doing is we are going to take the difference. So the first difference, so diff is a function in MATLAB which gives you the difference of the first of the consecutive variables. So here what will happen is, first of all I am just taking the first 3 columns because this is for translation. So I know the first 3 columns over here. The first 3 columns belong to translation, the other 3 belong to rotation, right? So what I'm going to do is the first 3 will be in translation and the next 3 will be in rotation. However, since these values are in radians, so this 4 to 6, these are rotation values but in radians. So what we do is we multiply it with 180 by pi to convert it to degrees. Okay, and we are taking the difference. So this is a function, diff function. So what it will do is, let me just execute and then explain it to you. So over here, if I open this and let me just keep both the files together. Right, so over here what happens is this first column, the first row over here is nothing but row 2 minus row 1 over here. So 0.0103 minus 0 will give you this thing. This minus this will give you this, and this minus this will give you this. Now this is for trans, so I have just taken the first 3 columns. Okay, now the second column over here will be third column, a third row minus second row. Third row minus second row will be this. So now this is very close to 0 because this is e minus 0.5, that is 10 raised to minus 5, and this is 0.0103. Hence this is in some sense 0 minus this thing, hence there is a minus value over here, and so on. So you get the point, right? You are taking a consecutive difference and putting this over here. So this is the main motive of frame-wise displacement. So how much is the displacement as the in between the consecutive frames? That is what we are looking over here. So that is for translation parameters. Similarly, we have for rotational parameters. So here the same thing is there for rotational. However, this is in degree. So we have also multiplied with pi 180 by pi. So that is one more thing. So we have converted to radians to degree. Okay. Now what we are doing over here is, here if you see rp diff trans into rp diff trans transpose. So what happens is this multi-p is a 151 cross 151 matrix again. So actually we had 152, but then because of this difference operation, what happens is, because difference needs 2 things, so finally we'll have 1 less. Okay, so I mean, just to give you perspective, no, not rotation, right. So if you see over here, second row minus first row will give you the first row over here. Third row minus second will give you the second row over here, and so on. You go for the last thing. So you 152 minus 152th row minus 152nd row minus 151st row will give you the 151st row over here. And then because you don't have the 153rd column, hence there is nothing to do minus over here, hence there is no 152nd row over here. I hope you understand. So basically here you'll only have whatever number of time points minus 1. Okay. So, and then you have done this. So the main reason for doing this is so that you know that diagonals will have the squared values. Again, one more thing. So now because this is difference, so we can say this is dx, dy, dz. Okay, because RP rest was x, y, z. So the difference can be dx, dy, dz because they are difference, consecutive difference. Hence, if you see the diagonals over here, it will be represented as dx square plus dy square plus dz square. Okay, you can just see that because so it is because of matrix multiplication. So the way matrices are multiplied, so this is multiplied by itself. Hence the diagonals will have square values and it will be the sum of the square values of all the three columns which are there. Remember, trans has only three columns, the first three translation parameters. So the diagonals will represent this. Now if we take the square root of the diagonals, then it will be square root of this. So this is in some sense the distance, the Euclidean distance of the motion. So FD trans is framewise displacement translation. So this is the actual displacement in Euclidean terms that we have. Okay. Similarly, the same thing is repeated for rotation as well. Only here there is d pitch square, d rho square and d roll square. That's all. So like this we have FD trans and FD rotate. Now what we do is we see what is the maximum translation. Okay, this is giving you for every different consecutive slice what is the rotation. So you can see FD trans and FD rotate are again 151 numbers. Now I'll see what is the maximum translation, and that will be stored in FD max trans. You can see 1.01 millimeter is the maximum translation and 1.5858 degrees is the maximum rotation that is there in this subject. Similarly, we can also take the mean translation and mean rotation. So here we have the mean translation. Mean translation is 0.1209 and mean rotation is 0.0545. Okay. Now, why did we calculate these parameters? So here now we can put a threshold. If suppose the maximum frame-wise displacement is greater than a particular threshold, or if the maximum frame-wise rotation is greater than a particular threshold, or if the mean is greater, a mean translation on mean rotation is greater than a particular threshold, then we will say exclude that subject. So this subject cannot be used because it is the motion is too huge, the motion is greater than the threshold. If it agrees to all these threshold, I mean if the parameters are less, then it will not be excluded. So as soon as I press step, so the program has ended. Now that's all. And if you see excluded, so over here the value is 0. That means over here the motion was not too much. So if you see all these numbers are lesser than these thresholds that are put over here. Okay, so now I have put a threshold of 1.8 millimeters. However, this particular subject has a voxel of 3 cross 3 cross 3 millimeter, if I'm not wrong. Oh, it's 3 cross 3 cross 4 millimeter. So this is the voxel size. So it is 3 cross 3 cross 4. So any value lesser than 3 over here will work. Any value lesser than 3 over here will work, because 3 is the maximum, 3 is the voxel size. So the motion inside the voxel, it is allowed. But if the motion goes outside the voxel, then it is not recommended. Okay, so you can have a different threshold over here. So now this actually depends on your data. So suppose you have 100 subjects and you put a threshold say 1.8, and say you have to reject 40 subjects because of that. So hence maybe considering a higher threshold is okay. Say if I take a threshold of 2.5, maybe then I have to only reject 10 subjects or maybe 5 subjects. Okay, so accordingly, because I have to do some analysis after pre-processing, right? So after pre-processing I should have enough subjects so that the results are meaningful, right? So we can actually decide the threshold based on your data set. So say out of 100 total subjects, say at least 80 subjects pass out that particular threshold. But again, the threshold should be less than the voxel size. You cannot have threshold greater than the voxel size. So if that is so if say 2.5, by keeping a threshold of 2.5, at least 80 subjects are passed out. That is 80% of data is at least uh, available after, I mean not excluded after this, then we can keep that as the threshold. So that is about the frame-wise displacement. So here in this video I have covered uh, first of all what is subject motion, we saw in the start, then we saw how to remove it, and then we saw frame-wise displacement, which will help you exclude or include a particular subject for your analysis. I hope this video was useful. Thank you so much for watching.